Okay, now find the frequencies of first, second, and third harmonics of a steel wire 1 meter long with mass per unit length of 2 exponent negative 3 kilogram per meter. Okay, kilogram per meter, and under a tension of 80 Newton. Okay, and then find the wavelengths of the sound waves created by the vibrating wire for all 3 modes. Okay, so what to do in the first step? First of all, identify which case is these questions. Is this a string, or is it closed pipe, or is it open pipe? So we look at here, it says steel wire. It's a wire, so it's about string. It's about string case. Okay, string. So string follow this one. String means it has 2 fixed end. Two fixed end. So we have 2 notes at the end, 2 notes at the end, and then amplitude in the middle, amplitude in between. Okay, this is string. Okay, and then he give you the length. Here you see 1 meter long length. So already all in SI unit meter. Okay, good. And then he give you the mass per unit length, which is mu. This is actually mu, mass per unit length. Already in SI unit, kilogram and per meter. That's good. So you don't need to change the unit anymore. And then under the tension, this is the tension T, Newton, SI unit. Okay, so he asked to find what? Find frequency of this one. This one is important. First, second, and third harmonics. So this is first harmonic, second harmonic, and third harmonic. What does it mean by harmonics? Harmonics is actually N. The N, okay? The N value. The N value, 1, 2, 3, that one. N value. That's the N value. So the first harmonic is actually N equal to 1. Okay, hold on a second. This N equal to 1. This second harmonic is N equal to 2. This third harmonic is N equal to 3. So harmonics is the N value. Okay, we will talk about this later on. So first of all, we need to draw out. If can, we need to draw out these first, second, and third harmonic. Let us first draw out. First draw out the wave, the shape of the wave for first harmonic, second harmonic, and third harmonic. And this picture will help us in solving the questions. Okay, so now let us start with drawing the first harmonic. Okay, let us draw it out. First, let us draw it out. Question A. So we want to draw out. Always remember, what is the fundamental mode of string? So for string, it always start with this fundamental mode. So for this type of question, you just have to remember the shape of the fundamental mode for string, closed pipe, and open pipe. You just have to remember this part. You just have to remember the first mode here. You just have to remember the first mode here, the shape of the first mode. Then it will help you. The first mode will help you to draw the second and third mode. Will help you to draw the first overtone and second overtone. This is the most priority. The first mode is the most priority. You must remember the shape of the fundamental mode for each type of the stationary wave. This is the string fundamental mode. This is the closed pipe fundamental mode. This is the open pipe fundamental mode. You need to remember the first picture. By using the first picture, you can draw the rest picture. Understand? Important is the first picture you need to know. Okay? So the fundamental mode for string is this one. It's like half wavelength. Okay, node to node. Okay, so let's draw it out. Yeah. So we begin with drawing the fundamental mode. Okay. So I want to draw a picture over here. Let me draw it out for you. Okay. So now, this is the picture here. This is the mode, which is the fundamental mode, first overtone and second overtone. And this is the number of harmonic, which is the value n. Okay, first harmonic, second harmonic, third harmonic. Okay, so you remember that string always start with this half wavelength. You see, half wavelength, node to node. Okay, so always remember the first one, then you can draw the rest. Understand? So okay, so this is the this is the node. Okay, I just want to draw the node here. Okay, so node from node to node. So this is the half wavelength. Okay, this is the half wavelength. Oops, sorry. So for what string is always start with half wavelength. Understand? Always start with half wavelength. So in the middle is the anti-node lah. This is the anti-node. Yeah. So from here, this one is anti-node in the middle. Okay. 2 fixed n is the node. This is the anti-node. Okay. This is the what we call the fundamental mode. Fundamental mode, and this is the first harmonic. First harmonic. Yeah. Just write as okay. Just write as n equal to 1. Yeah, harmonic 1, and then how about the second one? Falling below, going down below. We just add another half wavelength. Yeah, just plus another just plus another half wavelength. So we get this one still is the node. Yeah, this one is still the node. Okay, but in the middle now we have another node. So okay, so becomes like this. See that? Okay. Okay. This is, so we have anti-node here already. Okay. Yeah. And then going below, we have plus, and yeah, you see, it's always plus another wave half wavelength here, and also plus another half wavelength. Okay. So here, this is still the node. Okay, this is still the node. Now we have another yeah. Okay, so plus another half wavelength. Yep. So here is the anti-node, anti-node, and anti-node. Okay, so you see that this is actually from node to node is actually considered half wavelength. Okay, and then move down one mode is plus another half wavelength. So you got 2 half wavelength already. Okay, and then move down another mode is another half wavelength. So now you have 3 half wavelength. This is how we do it. Okay, you must know how to draw the picture. So always the first one is the most important. You remember the first one, then when moving down, you just plus half wavelength plus half wavelength. Okay, so so we can say the first one is always the fundamental mode. Yeah, how to this is a fundamental mode. Fundamental mode. And then going down is the first overtone. First overtone, and then moving down is second overtone. Fundamental mode, first overtone, second overtone. And the first one, fundamental mode, is always the first harmonic. Always the first harmonic. And then this is the second harmonic. And this is the third harmonic. Okay. First harmonic, second. Because why is it? Remember that. Remember this one also. For string and open pipe, both of these are all harmonic. All harmonic. That means the N only it has all number 1, 2, 3, 4, 5. Okay, all harmonic for string and open pipe only. Only the closed pipe. Closed pipe, it has odd harmonic. That means it has only odd number of harmonic. 1, 3, 5, 7, 9. So if you look at for string and open pipe, they have all harmonic. That means it just moved down with all number of n. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But for closed pipe, it only has odd harmonic. That means from 1, it straight away jump to 3. It don't have second harmonic. You don't have second harmonic. So from fundamental mode, go to first overtone, you go from first harmonic to third harmonic. Unlike the string, from fundamental mode go to first overtone, it still have second harmonic. This one jump to third harmonic. Okay. So for string is all harmonic. That means fundamental is a first harmonic, then first overtone is second harmonic. It doesn't jump to third harmonic. It is go to second harmonic. Second overtone is third harmonic. So it has all harmonic. So remember this one. This is the string. String. It has all harmonic. All harmonic. All harmonic means and it has all number n 1, 2, 3, 4, 5, and so on. Okay. So that's why we say from fundamental mode go to first overtone. It 1 go to 2. It doesn't go to 3. It go to 2, and then first overtone go to second overtone become 2 and go to 3. So fundamental mode, first overtone, second overtone, and it has all harmonic. Since it has all harmonic for string, okay, for string it has all harmonic, all number, all value of n. So it go from 1, 2, 3, and then so on, 4 and 5. Understand? This is important. This number is important. Yeah, you must know what corresponds to what. Yeah, what mode corresponds to what harmonic. Okay, so once we know about this, we can do the question already. So it gives you the mass per unit length and tension. So how to find the frequency? Okay, now okay, I just want to add another column. Okay, I want to add another column. I want to add the frequency here. Okay, I want to add the frequency here. Okay, okay, so the fundamental mode is frequency F1. Okay, F1, and then the first overtone, which is the second harmonic, means the F2, the second harmonic frequency, is 2 times the first harmonic frequency. Because frequency, the formula is Fn equal to Fn equal to n F1. Okay, this is the fundamental frequency. The harmonic is actually how many times the frequency of the first harmonic frequency. Understand? This is the first harmonic frequency. Second harmonic means it has frequency twice the first harmonic frequency, or twice the fundamental mode frequency. Twice the fundamental frequency. Okay, n equal to 3. n equal to 3, that means the frequency is 3 times the fundamental frequency. Second harmonic means it has twice the fundamental frequency. N equal to 3 means it has 3 times the fundamental frequency. Okay? Good. So now, after that, you need to know about this mass per unit length and the tension here. So what can these two values give us? We also remember the formula of this one. Okay, tension over mu square root, you get the speed of the wave in the string. Yeah, you get the speed of the wave in the string. So let's find out, yeah, the V, which is square root tension over mu. Okay, tension over mu. So tension is 80 Newton, and then mu is all already in SI unit, so no worries to change the unit. Okay, 2 exponent negative 3. Okay, okay, so let's find out the V. So let's calculate. So I got the value. V is equal to 200 meter per second. Okay, so I got the V already. Okay, I got the V already. So I want to find the frequency. So how to find the frequency? Okay, so how to find the frequency? So I look at the first one. I got the length of the wire, isn't it? This is actually the length of the wire from here to here. This is the length of the wire. Understand? For all 3 strings, the length of the wire is the same for all mode. So the length of the wire is 1 meter. You see that? It's 1 meter long. It's 1 meter long. Okay. So how to find? I got the speed already, so I can use the formula, the simple formula, which is V equal to F lambda. V equal to F lambda. I can find my frequency. I have the speed here. I have the speed V. Frequency, I need to find frequency, and lambda I just need to find from this relationship. The length equal to half lambda for the first one. See that? So we got the lambda already. Then we can find the frequency. Okay. So let's do it. Yeah, let's do it. Okay, let's do it. Yeah. Okay. Now let's find out the wavelength for all 3 waves. Yeah. Wavelength. The wavelength for the first wave is the length is equal to half lambda, isn't it? And the length is equal to half lambda. Okay, the length is equal to half lambda. Yeah, for the first one. So the length is 1 meter long. Okay, this is actually equal to half lambda. So what's a lambda? Lambda is actually times 2, so become 2 meter. Lambda is 2 meter. Okay. So we got the lambda, and we have the speed also 200. So what's the frequency for the first one? So the frequency for the fundamental mode, yeah, let's do it over here. The first one is equal, so we can find the fundamental frequency. So for the fundamental mode, maybe I just write at the top here. So for the fundamental, frequency, okay, fundamental mode. Okay, so I just use the formula V equal to F lambda. So the V is actually 200. I got from this calculation, 200, and then my lambda is 2 meter. So what's my frequency? My frequency will be 100 hertz. So I got my fundamental frequency, my fundamental mode frequency is 100. So I just write it down over here. This is 100 hertz. Understand? 100 hertz. Okay. So what's my second frequency? Second harmonic. Second harmonic frequency. Second harmonic frequency is twice the fundamental frequency. So it just times 2 of the 100. So I got what? I got 200 times 2 times 100. So I got 200 hertz. That's my second harmonic frequency. And then what's my third harmonic frequency? It's 3 times the fundamental frequency. Remember, the number of harmonic means how many times the fundamental frequency. Okay? So the third frequency is 3 times 100. So I got 3 times the fundamental frequency. Yeah, 3 times the first harmonic frequency. So I got 300 hertz. Okay. So is the answer correct? Yes, it's correct. Okay. The answer is 100 hertz, 200 and 300. You see that? 100, 200, 300. That's correct. That's correct. Okay, that's correct. Of course, you can find the wavelength also if you want. The wavelength is the same for all. Yeah, actually the wavelength. No, the wavelength is different. Only the length of string is the same. Yeah. So if you want to do the second one, yeah, this length is 2 times the wavelength already. See, 2 times the half wavelength. So it's twice the half wavelength. Okay, and then this one the length is 3 times the half wavelength. 3 times the half wavelength. So you can find their wavelength. Yeah, you can find their wavelength if the question asks for the wavelength. Okay. The wavelength 2 meter. Wavelength 2 meter is only for fundamental frequency. For the second harmonic and third harmonic, they have different wavelength. Okay, they have different wavelength, and because this one is twice 2 times the half wavelength, this one only one times half wavelength. This one is 2 times half wavelength. This one is 3 times half wavelength. For the same length of string, they have different wavelength. You can see, yeah. This one has the longest wavelength. This one has the longest wavelength. This one shorter. This one is the shortest wavelength. And then you go up the harmonic. You get a even shorter wavelength. Okay, getting shorter wavelength, but getting higher frequency. So what I can say is, what I can make a conclusion from here is, of course, if you look at here, yeah. Okay, maybe let us just substitute the value and find out. So this length is 1 meter. Okay, maybe let's find out. Yeah, let's find out one by one the wavelength if you can. Because the question asks, find the wavelengths of the sound wave created by the vibrating for all 3 modes. For first harmonic, second harmonic, and third harmonic. Okay, let's find out the wavelength. Now the question asks for wavelengths, lambda. So let's find out the wavelength. Okay, so for the second one, is it has 2 times the half wavelength, isn't it? 2 times the half wavelength. So it's still, the length is still 1 meter. Understand? Still 1 meter. So just put it 1 meter. This still is 1 meter, and then okay. So this is 2 times the half wavelength. So it become lambda. So this one is 1 meter. See that? The second harmonic, the wavelength is 1 meter. Last time the first harmonic is wavelength 2 meter. Now become 1 meter. How about this one? The total length is still 1 meter, but now it has 3 half wavelength. So okay, let's find out. This length is 1 meter. Okay, and this one has 3 times the half wavelength. So what's the wavelength now? What's the wavelength now? So find out. Wavelength now becomes 2 over 3. Yeah, multiply 2 divided by 3 meter. So which is what? Okay. Recording. Okay, so now this one I divide 2 divided by 3, I get 0.67 meter. See that? So is the answer correct? The wavelength 2 meter, 1 meter, 0.67. 2 meter, 1 meter, 0.67. That's correct. That's correct. You see that? The wavelength becomes shorter and shorter, but the frequency become higher and higher. So we can see what's happening here. The frequency is increasing. Yeah, frequency is increasing, but the wavelength is decreasing. You see that? The wavelength becomes shorter and shorter. But the frequency become higher and higher. Frequency become higher and higher, but wavelength become shorter and shorter. So it's actually because of this formula. So we can say as the wavelength, as it goes down, the wavelength become just put it over here. See here, this one. You can say this one, the speed is constant. The speed is constant, 200. This one is speed is constant for string. The speed is constant. But when you move down, because why the speed is constant? Why the speed of wave is constant? Because the tension of the string and the mass per unit length, the tension is in the string is the same. You are using the same string, so same mass, same length. Okay, so the mass per unit length is same. So that's why the speed is always constant. So when you are going down the mode, that means your wavelength becomes shorter and shorter. You see, the wavelength becomes shorter and shorter already. The wavelength becomes shorter and shorter. So that's why the frequency becomes higher and higher. And the speed is constant. The speed of the wave is constant. The wavelength becomes shorter, but the frequency becomes higher and higher. So this is what happened. Okay, so that's all for this question. Thank you. Bye.